Hi, I'm Julia White. I'm a PhD student in the Electrical Engineering Department at Stanford University, and I'm going to be sharing research performed in collaboration with my colleague Jessie Mew and our advisor, Professor Noah Goodman. So today I'll be discussing the results of our work with amortizing pragmatic reasoning. We care about the topic of pragmatics because language is often contextual, and as such, speakers and listeners require a level of pragmatic reasoning to communicate effectively. For example, if you were going to try to explain the third character out of this lineup of three faces, you'd probably want to describe it as the character wearing a hat, and you probably wouldn't say that it's the character wearing glasses, although that is literally true, because given the context, you can reason that saying this information doesn't disambiguate the third character from all the others. And this kind of reasoning is something that people are generally able to do very easily. So the big question motivating our research is how is it that people produce these pragmatic utterances? One popular model of pragmatic language use is presented by the Rational Speech Acts or RSA framework, which essentially postulates that speakers and listeners recursively reason about each other's mental states in order to communicate effectively. So let's consider a scenario where we have a speaker who's trying to indicate her friend out of the lineup you saw before. And in this scenario, our speaker can only choose one of three words, which are hat, glasses, or none. A naive speaker will attempt to maximize the probability that what she's saying is strictly true of the friend she's referring to, and this is the way that we tend to train image captioning models. So according to the naive speaker, in this case, both glasses and hat are equally valid options. And there lies the flaw in this approach. Because as I mentioned earlier, if our speaker says glasses, although our target is wearing glasses, given the context and that two characters in our lineup have glasses, this utterance would be kind of ambiguous for our listener. Whereas saying hat would distinguish the target with no ambiguity. And that path of reasoning is encapsulated in the pragmatic speaker. The basis of this pragmatic speaker is an internal model of the listener who she's speaking with. And with this internal model of her listener, she can consider which candidate they might select given her three possible utterances. She can reason that if she says none, the listener would select the first option. If she says glasses, the listener might select either the second or the third option. And if she says hat, the listener would select the third option. So clearly, she will choose to say hat. And essentially, in this way, a speaker can use pragmatic reasoning to communicate effectively in context, and that's the basis of RSA. But while RSA is able to successfully model lots of pragmatic phenomena, one shortcoming is that the naive implementations of RSA aren't scalable to more realistic settings where considering all possible utterances becomes intractable. In Mars levels of analysis, RSA is considered a computational account of language production in that it can reproduce what's computed to make these pragmatic inferences, but doesn't explain how people do this given the limited time and computational resources that come with real-time conversation. And to that end, we're proposing an amortized RSA as an algorithmic theory of speech production which explores the idea of speakers learning to amortize the cost of RSA computations by directly optimizing for successful communication with an internal listener model. In other words, our work concerns the question of whether we can build grounded language models that demonstrate pragmatics by directly training agents to communicate in reference games. And as such, can these models learn to amortize the cost of RSA computation? So now that I've established our motivation, I'm going to explain more in depth which models we explored. And to do that, we looked at speaker performance in the frame of a reference game. So formally, a reference game consists of two players, a speaker and a listener, and the speaker's goal is to communicate a target image from a set of images, while the listener's goal is to identify the target based on the speaker's utterance. And as for our models, I've split them into three categories. Those trained with language modeling objectives, models based on the RSA framework, and models trained with a communicative objective. So first I'll introduce the naive speaker, which is just an image captioning model that produces a sentence given some image. So ignoring context and given some reference game, we can use a CNN to embed the target image followed by an RNN decoder which generates an utterance. And then this model is trained with the standard language modeling objective to maximize the probability of utterances in the training data. And there's a pretty simple extension of this naive speaker, which we call the contextual speaker. And here we condition our RNN on the target and the distractor embeddings instead of just the target. Now moving along to our RSA speakers, we need to first define an internal listener model, which, given the set of images and an utterance, produces a distribution indicating the probability of each image being the target. So with that, to define our full RSA objective, this speaker is a distribution over all possible utterances given our reference game, and is proportional to the listener's surprisal as reported by this internal listener model, which is then balanced with the cost of the utterance, which we take as a linear length penalty. So plainly, we're enumerating all possible utterances and selecting the one that maximizes this equation. And this full RSA acts as our upper bound on the pragmatic quality of a speaker model. And our next RSA-based speaker is an approximation of that. So for more complicated settings, one solution to full RSA becoming intractable is to consider only a subset of possible utterances. And this is what we'll call the sample re-rank model, because we generate a set of candidate utterances from an image sampled from a naive speaker, and then, like with full RSA, we re-rank them according to an internal listener model. And lastly, I'll introduce our speakers, which used communication-based training. So here's our main proposal, which is this amortized RSA speaker. And for this model, we take a fixed pre-trained internal listener and try to directly optimize the RSA objective. And we do that by training with respect to this loss function, which you'll notice is essentially the RSA objective. So we're taking the loss with respect to the listener surprisal and the cost of the utterance. Essentially, this speaker has the exact same architecture as the contextual speaker, but varies in how it's trained. So we start with an untrained contextual speaker, and during training, feed the utterances our speaker generates into an internal listener model, and then update the speaker parameters by backpropagating to minimize the listener's surprisal and the cost of the utterance. And we're able to backpropagate through the discrete sequences our speaker produces using the Gumbel softmax trick, which essentially the idea is that if we have this distribution over tokens in a vocab and we want to take a differentiable sample, we can add noise and then take the softmax to make it look discrete. And then we're using a straight-through estimator, so we're discretizing the samples in the forward pass, but still treating this continuous sample as the original sample in the backwards pass. So we're able to backpropagate, but the listener is always getting a discrete sample. And finally, we used a black box reinforcement learning approach where we tried reinforce with a +1 reward for successful communication and a -0.1 for failure. And we've evaluated these models on 2 different datasets. The first of which is the shape world dataset, and this is an artificial dataset with images containing a single shape of a single color, which are described by artificially generated utterances with a total vocab of 15 words. And in this dataset, we have 4 possible contexts. Ones where the target can be identified by just its shape, ones where the target can be identified just from its color, ones where either the color or the shape are sufficient, and ones where both the color and the shape are necessary to distinguish the target. Then we have a real dataset, colors, which consists of color patches where the target is described by utterances generated from humans, resulting in a much larger vocabulary of around 1,400 words. And in this dataset, we have contexts where the color patches are very similar in hue or where the color patches are much more distinct from each other. And these are called close and far contexts respectively. And we evaluate the performance of our models on these datasets with respect to 3 metrics. First, we care about the effectivity of our speaker's utterance. So an utterance should serve its purpose in helping the listener identify the target, and we evaluate this by measuring the communication accuracy on held-out listeners that have been trained on separate data. Second, language should be concise. So given the context and how much info is necessary to disambiguate the target, we should modulate how much we say, and this is measured with utterance length. And finally, language should look conventional, and this was measured by the probability of an utterance as reported by an unconditional language model trained on utterances seen in the training data. First, let's look at efficacy. So here we can see the game accuracy of the ShapeWorld dataset, and since ShapeWorld is an artificial dataset with limited vocab, we can use the full RSA model, which again acts as our gold standard for pragmatic behavior and unsurprisingly achieved the highest accuracy. And then we see the amortized model does next best. And in particular, the amortized model does very well in comparison to the contextual speaker, which we see in the colors dataset as well. And because our contextual speaker and amortized speaker are identical in architecture, we can see that the communication-based training proved to be very effective. And in comparison to the reinforced speaker, which learns from a sparser communicative reward signal given by a black box external listener, we see an improvement in the performance with the addition of the explicit internal listener in the amortized model. And again in colors. Then looking at concision, we can see how length differs depending on context. So here are the average lengths of utterances produced in each of our game contexts and the breakdown of the average number of shapes and colors per utterance. And we see that when there's more information required, so these both needed contexts, the model uses longer utterances, which is seen most prominently in the RSA model, but is also present in the amortized model. And this pattern we don't observe as much for any of the other models in this dataset. And for the colors dataset, we see that humans do indeed tend to use longer utterances in the closer, more difficult contexts. And we can see that in this setting, the contextual speaker and the amortized model were the only models to demonstrate the significant difference in utterance length depending on the context. And finally, looking at conventionality on the colors dataset, we see that speakers trained with a language modeling objective do the best, followed by the RSA-based speaker, which is the sample re-rank model, which does worse. And then our amortized RSA, which does worse still, and this is potentially the result of language drift, where the model learns to sacrifice realism for communicative efficacy. So here are some examples of the language produced by these models for different contexts, and I've highlighted the kind of unconventional utterances that were produced by the amortized model for games on the colors dataset. And finally, on the ShapeWorld dataset, we tested our model's ability to generalize to unseen color shapes and color shape combinations. And here we found that the amortized model was second in performance only to full RSA. And again, we see the amortized model outperforming the reinforced and contextual speaker. But coming back to our motivation of finding a model that's more algorithmically plausible for real-time conversation, where there's limited time and resources, we see a large gap in the computational requirements for online pragmatic reasoning and amortized utterance production. So some takeaways that I want to leave you with are that first, the full RSA model is the gold standard at a competence level, but requires prohibitively large processing costs in realistic settings, while our amortized RSA model achieves performance close to full RSA in terms of efficacy, concision, and generalization, while being far more efficient. Secondly, when we look at the performance of our contextual speaker with respect to our amortized model, which shares an architecture but varies in that it uses communication-based training, it seems to indicate that some aspects of pragmatic communication are unattainable by simply observing surface-level linguistic cues. And lastly, our reinforcement learning approach shares the communicative objective with the RSA models, but was forced to learn from a weaker signal of success or failure, which resulted in poorer performance and might indicate that an internal model of the listener is necessary. So with that said, we've explored an algorithmic model that internalizes the explicit pragmatic reasoning of the rational speech acts models, and with this amortized model represent one answer to the question of how we produce pragmatic utterances.